Now, what kind of questions will you come across in chapter 4? You will come across balancing equations, and in chapter 4 you will see simple as well as complex equations. Why? Because at this point, when we come to chapter 4, we should be able to connect 3 or 4 concepts together. The first thing is, you might come across a question that does not give you the chemical formulas. For example, you might see a question that says gaseous nitrogen dioxide reacts with gaseous oxygen and liquid water to form aqueous nitric acid. Write out this equation and balance it. So what you are trying to do here is connecting 2 concepts. First, you are trying to remember from chapter 3, will you be able to convert name to formula? Right? So in this case, they gave you names: nitrogen dioxide, oxygen, water, nitric acid. How do you write nitrogen dioxide? You write it like this. How do you write nitric acid? It's written like this. So this was the knowledge from chapter 3. Right? And then you have to actually write the reaction out. So nitrogen dioxide, which is given as a gaseous compound, reacts with gaseous oxygen, which is like this, plus liquid water, which will be like this, to yield aqueous nitric acid, which is like this. Right? So this is knowledge from chapter 3. Now you balance this. How will you balance this? This will be balanced as 4 nitrogen dioxide. I'm not going through the process of balancing here. 4 nitrogen dioxide, 2 waters, and 4 HNO3. Okay? This is how we balance this equation. Okay? And this is a reaction which will test if you can convert names to formula and balance equation. But this is only a start of chapter 4. What you will see more here in chapter 4 would be that once you balance the equation, will you be able to actually work on stoichiometry problems. Stoichiometry problems. In other words, given 4NO2 plus O2 plus H2O, okay, just to make sure, let's check if this is balanced. 4 nitrogens, 8 plus 2, 10 plus 2, 12 oxygens, 4 multiplied by 3, 12 oxygens, 4 hydrogens and 4 hydrogens. So this is balanced. Once a balanced equation is given, will you be able to do quantitative conversions from grams to moles and work on stoichiometric problems? In other words, if amount of nitrogen dioxide is given, say, let's say in a specific reaction we have 0.3065 moles of NO2. If this is given, how many moles of HNO3 will be obtained? Right? So 0.3065 moles of NO2, every 4 moles of NO2 yields 4 moles of HNO3. So yes, you can obtain the amount of or moles of HNO3. The other type of problem, if 0.236 moles of oxygen is present, how many moles of HNO3 is obtained? Okay, 0.236 moles of oxygen. According to your balanced equation, 1 mole of oxygen yields 4 moles of HNO3. Okay, so then so many moles of HNO3 will be obtained. If we need to produce 0.3695 moles of nitric acid, how many moles of water is required? Again, similar type of conversion. We need to produce 0.3695 moles of HNO3. Every 4 moles of HNO3 requires 2 moles of liquid water. Right? So you can get moles of water here. So this is the simple versions of these stoichiometric problems. Now you may get complicated or a little bit more complex version of the stoichiometry problems. How does that look? NH3. This is just another example of another type of problem. NH3 plus carbon dioxide. So ammonia plus carbon dioxide. Ammonia is aqueous, carbon dioxide is aqueous, yields CH4N2O plus, and this is aqueous as well, plus liquid water. Plus liquid water. Okay. I'm going to show you one type of problem that might be asked, and then we will extend it. 136.4 kilograms of ammonia is present. 211, excuse me. 211.4 kilograms of carbon dioxide is present. You have these two ingredients in the lab. Okay. And when a reaction was done with this amount of substances, okay, how much ammonia will be obtained? Okay, that's the first part of the question. The first part of the question is how many kilograms, okay, how many kilograms of urea, this is urea, is obtained. So again, problem one more time. 136.4 kilograms of ammonia is present and 211.4 kilograms of carbon dioxide is present. First part of the question is how many kilograms of urea will be produced. So 136.4 kilograms of ammonia, this will be equal to, I think I'm going to write it here. This will be equal to 1.364 times 10 raised to 5 grams. And this will be equal to 2.114 times 10 raised to 5 grams. Okay. So 1.364 times 10 raised to 5 grams of ammonia. We know the mole ratio of ammonia and urea here, and when we balance this equation you will see that there is 2 moles of ammonia used for this reaction. So ammonia, molecular weight of ammonia is 17 point, let's see here, 17 point, so nitrogen is 14.01, 3.01024 is hydrogen, because every hydrogen is 1.008. So 17.03. So 17.03 grams of ammonia is 1 mole of ammonia, and these numbers I got from the periodic table. And from the reaction, every 2 moles of ammonia produces 1 mole of urea. Every 1 mole of urea is 60.06 grams of urea. I'm just writing urea instead of the formula. And every 1000 grams of urea is 1 kilogram of urea. This will be equal to 239.8 kilograms of urea. It's a long calculation. If you want to pause the video, pause it and take a look at it and go over it one more time. So here we were given kilograms of ammonia. We converted into grams because that's the only way we could convert it into moles of ammonia. And we converted to moles because that was leading us to moles of urea, because we have a mole to mole ratio here. From moles of urea, we went to grams of urea, and then we went to kilograms of urea. Now remember, we went to kilograms of urea because the question says how many kilograms of urea will be obtained. That's the first part of the question. Using the same method, we're going to find out that 211.4 kilograms of CO2, which in this case will be 2.114 times 10 raised to 5 grams of CO2, and every 1 mole of CO2 is 44.02 grams of CO2. And then every 1 mole of CO2 yields 1 mole of urea. Every 1 mole of urea, we've already seen, has a mass of 60.06 grams of urea. But we need the mass in kilograms, so 10 raised to 3 grams of urea has 1 kilogram of urea. So this tells us, from this calculation, we're getting 288.4 grams of 4 kilograms of urea. Now, since there are 2 reactants, and this is a very important point I want you to remember, 2 reactants. So we did 2 calculations. If there are 3 reactions and the amounts were given, we will do 3 calculations. If there are 4 reactants, we have to do 4 calculations. Okay, so after doing these 2 calculations, after performing these 2 calculations, you compare the amount of product, and remember, when you compare, both of them have to be in the same unit. So in this case we have kilograms. When you compare, you will realize that this is less and this is more, right? 239 and 288. So please make a note of this. The less amount of urea, okay, which is 239.8 kilograms of urea, is the theoretical yield. That means theoretically, this is the maximum amount of urea that you can produce. If you have 100% reaction efficiency, 239.8 kilograms is the maximum you can produce. Now remember, all the time there won't be 100% efficiency. Sometimes it will be less efficient, right? Because of several reaction conditions. The theoretical yield, this is the maximum that you can produce. And how will you get this number? You make the entire calculation layout in front of you, and then you compare the 2 yields of product. Remember, theoretical yield is for product, yield is for product. So you compare the yields of products from different reactants. You pick the lowest one. You pick the lowest amount of product, and that lowest amount, okay, just to make sure, I'm going to write it here. Lowest product yield. That you get when you compare both the results. Okay, that will be your theoretical yield. Now remember, reactions are not 100% efficient. So we move on to the second part of the question. What's the second part of the question? The second part of the question says, when 136.4 kilograms of ammonia reacted with 211.4 kilograms of carbon dioxide, 168.4 kilograms of urea was obtained or was formed or was produced. They might use any of these terms. You might see any of these terms, right? So much ammonia was obtained. This term is telling us that someone actually found out how much of ammonia was produced. Okay, someone found out how much of ammonia was produced. So what is that? Since it was obtained, since it was produced, right? This is the actual yield. Actual yield of the product, or AY, actual yield of the product. Okay, maximum we could have produced 239.8 kilograms of urea. We found that out. We could have produced 239.8 kilograms of urea if there was 100% efficiency. But so much urea was not obtained. They obtained 168.4 kilograms of urea. So what is the percent yield? What is the percent yield of the reaction? It's not 100%. If it was 100%, we would have found 239.8 kilograms. But we didn't find that. We found 168.4 kilograms of urea. So what is the percent yield of the reaction? Percent yield is equal to actual yield divided by theoretical yield multiplied by 100. So which is 168.4 divided by 239.8 multiplied by 100. Now remember, these two are in kilograms. Make sure that they both are in the same unit. So 168.4 divided by 239.8 multiplied by 100, and you get about 70.2% yield. Okay, 70.2% yield. So now they could make it, you could see this as a large problem where you have to work on this entire calculation, but not always. Sometimes you might be given both the actual yield and theoretical yield, and you might be asked to find the percent yield. Sometimes you might be seeing the percent yield and one of these two will be missing, actual yield and theoretical yield, and you might be asked to calculate one of these two. So depending on the nature of the problem, you should be able to calculate theoretical yield and percent yield given the actual yield. Or if percent yield and actual yield is given, you should be able to get the theoretical yield. Or given the amount of reactants, you should be able to get the theoretical yield. Now another important thing about this question is that we got 239.8 kilograms of urea from 136.4 kilograms of ammonia. But we also had in this reaction 211.4 kilograms of carbon dioxide. Now how much ammonia did we get from that? We got 288.4 kilograms of urea, right? So this was your theoretical yield, and this is a very, very important aspect of this. This was the theoretical yield of ammonia, but since ammonia was a key player in giving us the theoretical yield of urea, ammonia becomes the limiting reactant. What is the limiting reactant? The reactant, remember there are two reactants here, ammonia and carbon dioxide. Limiting reactant is a reactant that gave you the theoretical yield of the product, right? So when you compare the amount of product that you get from both the reactants, the lower amount of product or the lowest amount of product is the theoretical yield of the product, and the reactant that gives you the lowest amount becomes the limiting reactant.